This is Autoencoding Variational Bayes by Kingma and Welling, 2014. Presentation is by me, Daniel Brennan. I'm part of the CUNY Cognitive Neuroscience PhD program, and this course is hosted by City College Computer Science. We're actually going to start a bit backwards and looking at implementations of a generative model, such as a variational autoencoder, versus a standard convolutional neural network. One thing that a convolutional neural network is very good at is identifying features which are useful to the classification of images, for example. So a standard CNN can identify maybe the ear shape or the snout shape of these two animals and determine which of them is a cat and which of them is a dog, and with some high likelihood of probability of success. They're very, very strong algorithms. But one thing that a standard CNN cannot do is actually produce a new image of either of these classes. It's very difficult to for that algorithm to produce a new image that's realistic in any sort of way. And this is something that can be accomplished even by small children who are able to create with varying degrees of success drawings of different animals with the correct feature shapes and with minimal sort of motor skills, able to create an image that anyone could identify as either a cat or a dog. But at times there might be images that are sort of ambiguous in the middle. And so one might be saying that these children are sort of sampling from a distribution of features, a very complex distribution of features, when they choose to draw either a cat or a dog. And this is allowing them to sort of generate a seemingly endless amount of images which are correctly identifiable as either of those animals. And so this is the way that a generative model can work, is that you have sort of a latent space of features that you can just sample from and compile that together, and that will give you a realistic looking image, realistic data from a certain set of parameters that you can just choose at random. And so this is what's happening sort of under the hood. You might have a prior distribution p theta of z for cats and p theta of z for dogs. And then to generate an example cat, it would be p theta of x given z cats and p theta x given z dogs. And that's how you could generate either a picture of a cat or a picture of a dog. This is great until as long as we have the parameters theta, but unfortunately we only have x. We only have examples of these things. And so we actually want to sort of infer or learn the latent space in order to generate new images. Therefore, we want to find the posterior p theta of z given x. So z, our posterior distribution given our data. Unfortunately, the posterior here is intractable, and this is a very large problem. There's really no computational way to easily assess this posterior distribution. So the attempt here is to make things more tractable. One way that we can do this is we can approximate p theta of z given x. Past methods are Monte Carlo, which is more stochastic, but it just takes a really long time, and it's not very good. It's not very efficient with a lot of data, which we need to do if we're going to do deep learning. So one thing we can do is we can do q phi of z given x, which is an approximation to the intractable true posterior p theta zx. What's proposed here, something borrowing from information theory, is the KL divergence. And this is a measure of how well behaved our tractable distribution, q theta, is fit q phi is fit to p theta. How much shared information is them, or the reciprocal, how much information is lost by them being divergent. And so we want to minimize how much information is lost. And if we minimize this, we can say that our more tractable distribution is a better estimate of the posterior distribution, which is good for us. The connection to autoencoders here, that our tractable distribution can therefore be thought of a probabilistic encoder, and p theta of x given z as a probabilistic decoder with a loss function that incorporates the KL divergence for the encoding, and then just a reconstruction loss for the decoding. So the KL sort of keeps the latent variables in check, make sure that they're abiding by sort of a Gaussian or other Gaussian-like distribution that we can later sample from. And then the reconstruction loss is simply making sure that we're able to reconstruct our original image with some sort of success. There's only one last trick here, is that you can't do backpropagation through a random process. If we're sampling from a distribution, there's no way to sort of backpropagate, and there's no differentiation to be done. So we have to do something called the reparameterization. And so instead of z being a random sample of q theta z given x, which requires sampling, we're going to reparameterize as z is equal to the mu plus sigma times epsilon, where epsilon is a normal distribution centered at 0 with standard deviation of 1. And so what that's going to do is epsilon sort of does our sampling for us, and we can back propagate through mu and sigma. And so that's going to allow us to actually learn these parameters which we're going to put forward. And so what we can look at is an example of this in code implementation. So I've borrowed this code from this link here. What we're going to do is we're going to be looking at the MNIST dataset, which is very standard. These are just our hyperparameters, our batch size, and epochs. One thing that we're going to look at here is the network, the way that the network is laid out. So we're taking our inputs and we're doing just some convolution here and batch normalization. Finally, we're going to flatten it down, and then we're going to have a dense layer, which is going to feed into both a mu and a sigma here. And one thing that I want to emphasize, which we can think about later, is this latent dimension. So we're calling our latent dimension to size 2, which will be used later. So this is our encoder step. And then we're going to sample z. So we're going to sample from our mu and our sigma, which we've sort of boiled down with a dense layer into just 2 by 2. And then we're going to create our z's here using that. The next thing that we're going to do is we're going to do, this is the encoder, sorry. We're going to create the decoder. So the decoder is going to take the latent dimensions, which is 2, and then it's going to sort of do the reverse. It's going to bring this all the way up into a size which is analogous to our input. And here's the decoder summary. And so the entire variational autoencoder is going to be decoder run on the encoder. So the encoder is taking the input, and then the decoder is decoding that. And so the whole variational autoencoder looks like this. And we want to look at this loss very closely as well. So the loss is, as we talked about before, our reconstruction loss is just binary cross entropy. So that's just going to be a normal comparison loss here. And then the KL loss defined here is just going to keep the mu and sigma, well, it's going to keep z as something that appears to have been sampled from a normal distribution. Okay, and so we can compile that with an optimizer, and we're going to use this KL reconstruction loss, which is both keeping keeping z in check, and it's also making sure that we're reconstructing effectively. We're going to train that with 100 epochs, as I've done, and then we're going to visualize. Remember when I said that the latent variables were 2-dimensional, so that's going to be very important when we're looking at this visualization. And so we have the 2 dimensions here. We have the first and the second dimension. And within this sort of latent space, you can actually see sort of a structured nature going from 1 over to 0. And throughout the different numbers here, you're actually seeing a structured representation, quasi-semantic representation even of these different numbers. and there seems to be some sort of latent space, which is, straighter lines to the right and more curvature to the left bottom here. And that's what you can accomplish with a variational autoencoder. And this is all due to the work of this paper. Thanks.